Hi, in this mini lecture, we're going to look in detail at this idea of approximating the area under the graph of a function by a sequence of rectangular strips. Okay, so these approximations go by the name of Riemann sums. So the aim then is to look very carefully at how we build up these approximations. So I'm going to outline the theory for how we would calculate one of these Riemann sums given a function. And then the next mini lecture, I'll go through a couple of examples. Okay, so the idea, and this underpins everything that we need to know about integration. The idea is that we start with the function, we start with the graph of a function y equals f of x. We have its graph there, that's the red curve that's showing. And what we'd like to do, what we're trying to do, remember, ultimately, is come up with a sensible way of defining and measuring and calculating the area under the graph of f between 2 points x equals a and x equals b. The basic idea is that we can approximate this area by a sequence of rectangles. Areas of rectangles are really easy to calculate, so this is a good practical way of calculating that area, or certainly of approximating it. And that's the task now, is to understand exactly how this approximation is built up. What are the different elements to it? Okay, so I'll go through the ingredients that we need to build up this thing. Well, our starting point is a function f. Its graph is shown. It's going to be defined on a closed interval ab. So stretching between x equals a and x equals b. And we're going to be looking at functions f of x, which are non-negative. Okay. That's going to be our starting point, and then we can expand out to essentially any function. So those are the first two ingredients, the function f defined on a closed interval ab. The next step for building up a Riemann sum is basically to split up the interval ab by using a sequence of points that we call a partition. And it's this partition that's going to tell us where to put the rectangles. Okay, so we introduce what's called a partition of the interval AB. So what that involves is taking the original interval AB and splitting it up into a number of subintervals. Now we do that by starting at x equals a, and for notation reasons, I'm going to call that number x equals a. I'm going to call that x0. Then I move to the right and identify an x1, move to the right again and identify an x2, an x3, an x4, an x5, and so on until I get to the end. And the last one I'll call xn. So in this case here, I've tried to represent the general idea of using n subintervals. Now, obviously, there is an actual number of subintervals there. You can count the dots, see how many. But in general, we talk about having n subintervals. N can be any number. Okay, so we choose those numbers, x0, x1, x2, and so on up to xn. The first one called x0 is a, the last one called xn is b, and that gives us a partition. So very much aligning with the everyday use of the English word partition, we chop it up in this way. Okay, I've labeled here two in the middle, which are going to be generic points of this partition. So we'll have to talk about the general point of a partition xk. So the k here is somewhere between 0 and n. Okay, so that's our next ingredient then, this partition, where we take the interval and we chop it up using a sequence of points into n subintervals. So our partition is this set of numbers, x0, x1, x2, and so on up to xn. The first one, x0, is a. The last one, xn, is b. x0 must be less than x1. So we have this strictly increasing list of numbers. So x0 is to the left of x1, which is strictly to the left of x2, which is to the left of x3, and so on until we get to the last number, xn, which is equal to b. So that gives us these n subintervals, the first one being from x0 to x1, the second one from x1 to x2, the third one from x2 to x3, and so on. The general interval, the kth interval, starts at xk minus 1 and finishes at xk. Okay, so for future reference, it's good to have those labels for us to be able to use. Part of the discussion will involve the length of each of these subintervals. Well, we can determine that by straightforward subtraction. So the length of the first interval, we call that delta x1, and that will be simply the distance from x0 to x1. The length of the second subinterval, we'll use the label delta x2 to describe that, and that will be x2 minus x1. So we're simply measuring the distance between successive points of the partition. The length of the general, the kth subinterval, as you can see written down there, is delta xk, and that will be the right-hand value xk, take away the left-hand value xk minus 1. Just want to be careful there. That's a subscript k minus 1. It's not the number xk with 1 subtracted from it. We need to define this thing called the norm of the partition. The norm of the partition is going to tell us the difference between a partition that has very wide rectangles and a partition that has very narrow rectangles. The norm of the partition we can define as being the width of the largest subinterval. Okay, so no matter what size all of the other subintervals are, what we want to know in terms of the norm is the size of the largest subinterval. And this makes sense in a way, because if we know the size of the largest one, well, we know then that all of the other subintervals are smaller than that. So really, it's the size of the largest one that counts. It's the size of the largest one that tells us the difference between having a partition with wide rectangles and a partition that has narrow rectangles. We want to know the size of the largest one, and we call that the norm. Okay, so we have a function, we have an interval AB, and we have a partition of that interval. Let's zoom in now and start building the rectangles. So with our partition in place, we can now start putting in these rectangular strips that are going to actually form the approximation to the area. We want each of those strips to reach the graph of F. Of course we do, because we're trying to approximate the area under the graph. Okay, so we don't want to draw, little short rectangles. Let's say here like that are nowhere near the function. That rectangle has got nothing to do with the area under the graph on that interval, nor do we want to draw rectangles that miss the graph. Let's pretend that's a rectangle there, if you don't mind. We don't want to deal with rectangular strips that completely miss the graph. Okay, so neither that small rectangle there, nor that great big one give us anything closely related to the actual area under the graph on that part of the interval. So what we need then is a rectangular strip that's standing on, as we call it, standing on the kth subinterval there, as we see between xk minus 1 and xk. And the way we do that is we choose some number ck. We choose a number, any number, from the kth subinterval. So we pick any number in the kth subinterval, and we calculate the value of the function at that point. On the graph, where will that be? That will be that point there. So that point there on the graph is at height y equal to f at ck. So we've picked any number in the subinterval, call it ck, because it's coming from the kth subinterval. And then we draw a rectangle whose height is given by f of ck. So that's what's shown there in the diagram. As you can see, I've labeled that. The height, we call it h of k, and the height is given by the function at the point in question. How do we choose ck? Well, we'll see a few different ways of doing that, but fundamentally, we can choose any number ck from this subinterval. Okay, so there's our fourth element. We have the function, we have the starting interval, we have the partition. On each subinterval, we draw a rectangle whose height is determined by the function. Okay. So the rectangular strip, as I've said, it meets the graph of the function f at the point x equals ck, y equals f of ck. And we say that this kth strip stands on the kth subinterval. What's its area? Well, here's where the fact that we're using rectangles comes home to roost, because the area of this rectangle is really easy to calculate, because it's just the height, hk, times the width, delta xk. The height is f of ck, the width of the interval is what we've called delta xk. Okay, so we know how to calculate the area of each of these rectangles. We pick a CK, we calculate F at that point. That's the height of the rectangle. The width of the rectangle is delta xk, which we'll have written down essentially already. Okay, and then we carry out the last step. So we have all of our ingredients in place now. The Riemann sum then is what we get when we add up the areas of all of those rectangles. So there's our definition. It's a big long definition. It involves all those different ingredients. So a Riemann sum then is what we get when we start with a function on an interval AB. We introduce a partition. We pick a point from each subinterval. We calculate the area of the rectangle whose height is given by the function value at that point for that subinterval. And then we add up all the rectangular areas. There isn't a unique Riemann sum. There's lots and lots and lots of Riemann sums, because if you give me a function f and an interval AB, well, I could have lots of different ways of introducing a partition. It might have 5 points in the partition. It might have 10. It might have 1,000,000. We can have lots of different points in the partition, lots of different partitions. Likewise, even when the partition is fixed, there's lots of different ways that I could pick the CKs to determine the height of the rectangles. So in the example shown here, the height of the rectangle is determined by using, well, I've used the midpoint of each of the subintervals. You can perhaps see that the height here, where the graph hits the top of the rectangle, is halfway along the top of the rectangle. That's because in drawing this diagram, I used CK to be the midpoint of each subinterval. Okay, so if I change any of these choices, if I use a different partition or a different choice of CK, I'll get a different Riemann sum. But they're all fundamentally that same thing, just adding up areas that touch the graph, of rectangles that touch the graph. So here's a different choice of CK. So I can hopefully see there that in the second example, I've used the same partition, but I'm using different CKs. In the second example here, you can perhaps see that I've used the CK that makes the rectangle touch the graph at the left. So rather than touching the graph at the midpoint, the rectangles are touching the graph at the left-hand end of the subinterval. And that's a legitimate choice. Third example, here I'm using a different partition, but again, following that rule that I construct the rectangle by using the CK that's at the left of the subinterval. Okay, so, well, we have our definition in place. That's the key thing. We need to look at the formulas for these things so we can actually do some calculations. So what have we got here? What's going on here? Okay, so Riemann sums are what? We're going to add up the area of each rectangle. Okay. So if I look at that first rectangle, what's its height? Well, I've picked C1 for the first interval. The height, H1, is f of C1. And the width of that rectangle is what I call delta x1, which is always going to be x1 minus x0. Okay, so the area of that first rectangle, I suppose we could call it A1, is going to be f of C1 multiplied by, that's the height, by the breadth, delta x1. So that's the area of the first rectangle. The area of the second rectangle, A2, will be f at the C2 from the second subinterval times delta x2. They'll have a similar for A3, for A4, for A5, and so on up to AN. Okay, so there's my formula for the Riemann sum, and I'll use an SN for the Riemann sum. S for sum, N because I'm using N subintervals. So there, as I've just written down a moment ago, there's the area of the first rectangle, there of the second rectangle, there's the area of the third rectangle, there's the area of the last rectangle. And we simply, I suppose I could say, add up those areas to get the overall Riemann sum. Okay, so if I were to say that in words, what would I say? I'd say add up this number, f of ck times delta xk, starting at k equals 1 for the first subinterval, the first rectangle, and ending at k equals n for the last subinterval, the last rectangle. And the mathematics that's written down in the very next sentence there, in the next line, I should say, is simply putting into mathematical notation exactly the words that are in the previous sentence. Okay, but it's perhaps new notation for lots of students. So let me go through that. So add up. Those words add up are translated into this symbol here. This is sigma, a Greek capital S, S for sum. So that's read as sigma. Like I say, it's a Greek capital S, S for sum. So when you see the words add up, that corresponds to the symbol sigma. Or I should probably say that the other way around. When you see the symbol sigma, that says add up. The next elements, so add up is translated into that sigma symbol. Then the next bits, starting at k equals 1, ending at k equals n, we use this notation to tell us where to start and where to end the sum. Okay, so we have sigma, says add up. Where do I start? We start at k equals 1. Where do we end? We finish at k equals n, as indicated below and above the sigma symbol. And then the last part is, well, what are you asking me to add up? And that's indicated after the sigma symbol. So we're adding up this quantity here, which we give down here. And the notation then tells me sigma for add up, start at k equals 1, finish at k equals n. So what would that give me? Well, if I add up this quantity here, I can see that it depends on k. So this formula depends on k. The instruction is telling me add up this quantity here that depends on k, starting at k equals 1. Okay, so I'll start at k equals 1, and I'd have, well, there's that object with k equals 1. Then I do the next one. So I haven't been told to stop yet, so I'd do it for k equals 2. And I keep doing it until I get to the end of the sum, which I'm told was at k equals n. Okay, and I'd probably be told that n is 5 or 10 or 100, so I know where to stop. So this is a particular example of a general bit of notation we use in mathematics, and hopefully you recall now that I see sigma, that stands for add up, start at k equals 1, finish at k equals n. What am I adding up? I'm adding up whatever the symbol UK represents. Starting at k equals 1, U1. Add on k equals 2, U2. Add on U3, add on U4. Keep adding until we get to the last one, UN. Okay, so the important thing there, okay, there's a bit of notation that's perhaps new and that needs a bit of getting used to, and you'll have plenty of opportunities to get used to that as I go through the next bits of the material. But really the key thing here is knowing how to build a Riemann sum. Start with the function on the interval AB. Do the partition, so choose your points. Pick a C, a C1, a C2, a C3 from each subinterval. Calculate F. Calculate the area of each rectangle. Add up the areas. We look at an example now for a reasonably simple function so that the complexity of the function F doesn't interfere with the other complicated tasks that we have to deal with.